I like to start here. I like to start here because this is the picture that the Voyager probe took of our tiny pale blue dot hanging in the universe and all that vasty darkness. It's tiny. And it was Carl Sagan who actually told NASA to just turn Voyager around and stop taking pictures of the undiscovered and look back at our home. This is our home, and it's blue. It's blue because we are not really planet Earth. We are planet ocean. 72% of the Earth's surface is water. 72%. So really the land bits are maybe that's where we live. So it's very important to us, but it's not the most important part of our Earth or our climate. So I'm really glad you're here today. And I wanted to show you this. This is our planet. And everybody looks at this, my students, my colleagues, they say, oh, what amazing satellite data we have. Look, we can see ourselves. No, that is math. That's a simulation. That's math and supercomputers doing our Earth system, not just our weather, but also our oceans and our land surface and all of the gases in our atmosphere and the biogeochemistry of our ocean, where all of the carbon goes. We have every drop of water, every photon that comes in from the sun, every tiny little molecule of carbon. We keep track of them in an Earth system model. And we've come a really long way. I sometimes get, and why do we need these unbelievably sophisticated models? I once had a conversation with the head of Amazon Web Services, and they said, you have won a climate grant of a whole bunch of CPU time to run your climate models. I was like, great, how much you give me? And they were like, well, we're going to give you 10 million CPU hours. I was like, great, I can run my model for a grand total of 600 years of model time. Well, that's not enough. He said, what do you want? I said, I want 20,000 processors for a year. He's like, he turned kind of white. It was bad. Like, okay, fine, I'll rein it in. But this is why. This is the atmospheric CO2. And it starts in 1958 by this guy, Dave Keeling, who was one of my professors when I was at Scripps. Very, very, very nice man and an incredible scientist. This curve is now carved on the wall of the National Academy of Science in DC. You can go see it. It's right in the foyer. And it deserves to be there because this guy started that CO2 measurement both at Mauna Loa, which is the top of the volcano in Hawaii, and at the South Pole. And that together, and you're seeing the red line is the South Pole and the black line is, and for all of your, friends and crazy uncles who go, oh, it's the volcanoes. You show me where Mount Pinatubo blew on this plot. Now El Chichon, now Agong, can you see them? No, you can't, because the amount of CO2 that we spew out with everything we burn, whether it's coming out of your tailpipe, out of your power plants, out of your backyard fire, everything we burn actually adds carbon dioxide to the atmosphere, even plastic. All of it ends up being CO2 oxidized. So I just wanted to show you this because it's having, oh, and in case anybody actually, so despite all the shutdowns, CO2 kept increasing because it's not the only carbon cycle component. There are others that kicked in natural carbon that was released to the atmosphere. And I'll give you 10 points of extra credit if you can guess what the two sources were. When we shut down, what happened? Well, we ended up with a whole bunch of forest fires. Burning trees is adding CO2 to the atmosphere. We also ended up with a whole bunch of warmer water in the ocean, which degassed a bunch of carbon dioxide. So the combination was we saw it's kept growing, as you can see. So what happened to the atmosphere at the same time? Well, we've seen record warm years in a La Nina, which should be when the ocean is actually a little bit cooler and is taking up a little more carbon dioxide. But no, that's not what happened. So we see these profoundly different anomalies. And here in Arizona, and I live out here in Tucson, and I work at the University of Arizona, we have some very specific climate prediction needs. These are extreme summer heat. You can see it going up. This is the biggest growth in summer temperatures is right here in Arizona. You can see how many more days of heat we have, how much our Lake Mead water levels are dropping. Notice the bathtub rings out here. And this is our long-term drought index. These are the floods we had from our summer monsoon. It's a lot. It's a lot living here. We're kind of in the hot seat. And you can see this is half of the country. I know it's hard to remember when you live in New York, and there are so many important things going on in New York, but half of our country is in extreme drought at the moment. And I just want to point out too that our Lake Mead is at its all-time low since it was filled. If it drops much further, the outflow will be too high in the basin, and we won't be able to get any water out for California, Nevada, and Arizona. So this is a really big deal. But even with that big increase in warming and the drought and all the rest of it, that is only 3% of the energy imbalance that's been created by that carbon pollution blanket that we have spewed out. All of that atmospheric CO2 is one of our greenhouse gases. So the sun shines in every day, it warms the surface of the earth, and that heat tries to re-radiate back out as long wave radiation. And it's blocked by certain kinds of gases like water vapor, methane, and primarily carbon dioxide. So and what happens is only about 3% hangs out in the atmosphere. Most of the warming is actually in the ocean, 93% of that energy imbalance. And how do we know there's an energy imbalance? I'll just tell everybody. It's because of IRBE. Our Earth's Radiation Budget Experiment is a series of satellites that sits out at the edge of our atmosphere and looks out at the sun and in at the Earth. And IRBE tells us that every single year we have this about the same amount of sun coming in and less getting out. So where'd it go? Because not every year is our hottest year in the atmosphere. Where did it go? Well, 93% of that energy imbalance that everybody tells us about went into the ocean. And all of the blue here is ocean. And this tiny little pink line, which you can barely see, that's the atmosphere. It's doing incredible damage. We've had spectacular climate damage just this last year, whether it was droughts, floods, heat waves, fires, the Great Barrier Reef bleaching, sea level rise. All of that was happening this year. A lot of it very damaging, just tragic. But in fact, that's only 3% of the energy imbalance. Okay, so the ocean warming goes every year. This is spectacular. The world's oceans were the hottest ever recorded in 2020, and we just saw a report out today from NOAA that says that no, 2021 is the hottest ever. I'm sorry I didn't update the slide already because it just came out this morning. And this is also, what's exciting is what we're doing together. So this is the UN, the United Nations Decade of the Ocean, the science we need for the ocean we want. And they've got a whole framework and a bunch of key challenges, et cetera. It's never my favorite because it's very people focused and I'm very ocean focused, i.e. I am less interested in my coasts. I know I should be, I would be if I lived in Manhattan. But in fact, let's talk about carbon. Let's talk about that carbon pollution blanket and all the heat that it's driving into our oceans and into our atmosphere and all the damage it's causing. It is actually the law of the land that carbon dioxide must be regulated by the Environmental Protection Agency of the United States as a pollutant. The Clean Air Act's sweeping definition of air pollutant included any air pollution agent or combination of agents, including physical, chemical, substance, or matter, which is emitted into or otherwise enters the ambient air. Without a doubt, physical and chemical substances, which are carbon dioxide, the statute they ruled is unambiguous. And you can see the ones that ruled. This was back in 2007 and April 2nd. And there was a scientist brief in support of the plaintiffs, Massachusetts and 12 other states. It was the scientist brief. And I'm one of the 13 scientists that wrote that brief that just said the science is solid. We know this really well. And so they asked, may the EPA decline? And does the Clean Air Act give the EPA authority? And the justices ruled yes. They may not decline, and yes, it is covered. So it's already the law of the land. And in fact, if you look at our atmospheric CO2 emissions for the United States, we actually started cutting our emissions in 2007. That was our peak emissions, was about 6 months after that ruling. And we're now down almost 20% on our total global emissions. I think I have a plot here. But now we have this Paris Agreement. So how do we verify? How do we figure out where all that carbon dioxide is going? It's not all hanging out in the atmosphere. So about 85% is coming from fossil fuel burning, and another 15% from clearing of forests and land use changes, basically. And about 46% hangs out in the atmosphere, and about a quarter hangs out in each of the ocean and the taken up by growing things, by green plants. So, sorry, plants are always green, but so what I wanted to do is 72% of Earth's surface, 1 out of 4 molecules of carbon dioxide that comes out of anybody's tailpipe anywhere in the world goes into the ocean within a year. So, but where and how fast? Because we don't monitor, it's very hard to go to sea. So we wanted to reduce the uncertainties here, partly because we have a whole bunch of colleagues and friends who are looking at carbon dioxide removal using the ocean. And you'll see a whole bunch of these marine geoengineering type of activities, all of which are the in part. But I told you about how much CO2 degassed during our pandemic year. Yeah. What happens if it comes back out of the ocean is a really big challenge. So here's the ocean carbon uptake. We've got a biological cycle because all or living things make their body tissues out of carbon. And a solubility cycle where the gases can dissolve more in cold water than they can in warm. And if there's an overburden of carbon dioxide in the atmosphere, it will dissolve into the ocean. And since we keep burning things, there's always an overpressure. So and here's the complicating factor. So if it were just the solubility, just the biology, one might focus on what kinds of ecosystems are being affected. But in fact, it's windier. That energetic atmosphere, this is actually the change in wind speed over 30 years. From 1985 to 2018. And what you'll see is there's only a few blue dots out here in the middle of, kind of over by Papua New Guinea. The whole rest of the world in the ocean is windier. Yeah, so windier means more stirring. More stirring means more mixing. More mixing means more CO2 could come right back out. Now, at the moment, more is going in, but that could change. And so where we're looking for all these winds, now you might say, okay, so there are westerlies here in the north, there are westerlies in the southern hemisphere, and then there are all these lovely easterlies. But when you showed me that plot, it sure looked like all the winds were increasing. Yeah, they are. Both the easterlies and the westerlies in the northern hemisphere and in the southern hemisphere, everybody is increasing. And the reason is climate change. This is a dynamic effect, and it is stirring our oceans. Not only do we detect it because of the change in the wave heights over the global ocean, we detect it by looking from satellite using a scatterometer where we bounce radar off of the wave. And if it attenuates the beam, that means the wave is very high. Our wave equations are really, really excellent. And I say that because the initial development was by Walter Munk, who was the last call that Eisenhower made before D-Day, because they needed the weather to be bad enough to keep the Luftwaffe off their backs, but not so bad that it would swamp the boats with too big waves. They had very low gunnels and drown our soldiers. So these wave equations are crucial, and we're still using them right here on this plot as we did then. They've gotten even better, but it was pioneering work and really important. So now, what is it doing to our ocean? This is an ocean plot, and you can see everywhere it's blue, it's where the mixed layer of water at the surface is getting deeper. Now, some of you, any of you who may have heard of the IPCC, the Intergovernmental Panel on Climate Change, whenever they discuss the ocean, they always say, oh no, it's going to get warmer and it's going to stratify. It's going to get less mixed. And that would be true if the only thing that were happening were just the heat. But recently, in the last 20 years, the winds have picked up so much that in fact it's getting deeper. Now you can still see a few red spots over here in the tropical Pacific, but primarily most of the globe, it's getting deeper because of these stronger winds. So what I really want to do is I want to look at the winds, and you can see these swirling over our ocean in this animation. And what you're seeing is the red is where it's outgassing and the blue is where it's going in. I know, look at that. This is a simulation again. This is not actually real data. And what I want is real data. I want to be able to verify what the ocean is doing so that we can verify our agreements, our Paris Agreement, et cetera. So how exciting. How do we do this over a global ocean that's 72% of our Earth's surface? And did you know research vessel, one of these 300-foot ships that my students and I have been go out to sea to measure things on, they cost about 50 grand per day bare boat. So 2 days, you can get about of the profiles where you lower a big array of water bottles over the side and you fill them at different depths. Those you can get about 5 of those profiles every 2 days. So for about 100 grand, you get 5 profiles. I'm going to show you another option. So going to sea is hard. It's long days. I don't know if you've read 2 Years Before the Mast or, Moby Dick or something, but whether, or maybe you've been out on a cruise or something, but or been fishing, this is, or maybe you do round the world sailing race. Being away from home is really tough. And if you didn't bring it, it's not there. And not only that, but things break all the time, the bashing of the waves and people, equipment, your boat, it's tough. And this was all the measurements. This is again an oceanographer spot. So the gray is the continents. Here's Australia, here's Russia, here's the United States. This is all the measurements that researchers made between 1999 and 2015. 16 years worth of measurements. That's all we have. Notice all the white area, especially down here in the Southern Ocean. All that white area, not one measurement was made. So how do we know where all that heat is going? How do we know where all that carbon is going? How do we get there? The secret is, and it's not a secret, even though this is a secret science club, it's robot floats. Robot floats are how we do it. They're cheap. They last for 5 to 10 years. It's better batteries and better microsensors that use less power. So we can actually have, and this is what it looks like. The measurements from robot floats called Argo floats, over 1.5 million measurements over the entire ocean. Yes, in the same time period. And we really only the community only started deploying these floats in about 2004. So you live, I know no one knows this because there's so few oceanographers. Did you know there's only about 6,000 PhD level research oceanographers in the world working today? 6,000. Yeah. About 3,000 of them do things other than marine biology. It's I think, frankly, and there's 60,000 meteorologists in the United States. 6 million people with geological credentials, but 6,000 oceanographers in the whole world. There aren't very many of us. It's the thinnest of thin blue lines. And so we use robot floats. I'm going to tell you about the program we got funded called the Southern Ocean Carbon and Climate Observations and Modeling. These original Argo floats, they just measure temperature and salinity, and they can only go to 2,000 meters. The new floats, there are these deep Argo floats, can go all the way to the bottom. And the floats I'm going to tell you about are biogeochemical floats, are carbon-sensitive floats that can also measure plant food like nitrate and oxygen in the ocean, which is also changing, which is basically getting a look at the health of the ocean and how much carbon it's taking up. And we got this funded in 2012. This is Jorge Sarmiento, my colleague from Princeton. I left Princeton in 2006 to join the University of Arizona, and that's why we still have this collaboration. And this is what a SOCOM float does. Here it is. Biogeochemical, I know it's a huge word, but it's because it covers both the biology, the geology, and the chemistry of the ocean. And what you'll see is that's what it looks like, these yellow tubes. Why yellow? Because yellow is, red is absorbed better by ocean water, so you can see it for longer. It's more likely you'll be able to see your float. These are entirely passive. They have only ballast to get them up and down. And there's a really good reason for this. One, it's incredibly power efficient to do these profiles. And two, they are, the law of the sea says, if you drive something, an AUV, a ship, an ROV, anything, if you drive it into someone else's exclusive economic zone in the ocean, you have to have a permit. But if it drifts in, it's legal. floats just drift. So the reason we can cover the entire world without a permit is because it's a float, like a message in the bottle, except it has 6 different microsensors on it, in addition to pressure, temperature, and salinity. And every time it pops its head up above the ocean, every 10 days, it beams its data directly via Iridium satellite back to home and is loaded up on the web within 2 hours. In fact, it's part of the global telecommunication service, which is how we get all our weather data. So this is how we actually have built a program that and I'm actually going to show you this. The old way, these huge array, it weighs when it's full of water as much as like a VW bus. It's very, very heavy. Once upon a time, we had a grad student who grabbed the array. Don't grab the CTD. Don't grab the CTD. It's too heavy. And it literally yanked him off the deck and into the ocean. He shall remain nameless, but that it's very dangerous. They're very large. And then we take 1 million little samples, and then we use all of the equipment in the labs and then we bring some of them home to base, but many of them we run right there while we're at sea in real time. There you go. We're replacing some of that. That's my student, Becky Beedling, who's now a research scientist. Excuse me, I got something in my throat. At the Geophysical Fluid Dynamics Laboratory at NOAA. So that's where we're headed. And this is the actual trajectories of all of these floats. We've deployed over 200 now, and we will deploy another 100, 130 before the end of the program. So, and those last for 5 years and will give us about 200 profiles, and they cost less deployed than 2 days of ship time. So it costs about $80,000 per each of these floats, which sounds expensive, but I will get 250 profiles from these rather than the 5 that I would get if I had to do it just by ship. It's a revolution in oceanography. There's been nothing like it basically ever. This is humanity's first best, closest look at how our ocean moves and changes in real time. So this, I just wanted to show you, this is how an oceanographer looks at the ocean. The Southern Ocean around Antarctica basically is the blender, the big mixer of all the water in all the world's ocean. It's the hub. Everything else where you can see our Atlantic Ocean stretching off and all the way to the Arctic, our enormous Pacific Ocean, our little tiny Indian Ocean, all of it mixes around Antarctica. So Antarctica has become the Southern Ocean, which is National Geographic says it's our, it was just declared just this last year to be a real ocean, even though oceanographers have been calling it that forever. But the Southern Ocean takes up about 50% of all the carbon dioxide absorbed by the world's ocean, even though it's relatively small, and about 75% of all of the heat. Now, think about that for a second. 93% of the energy imbalance of the planet goes into the ocean. And of that, 75% goes in around Antarctica. So when I tell people that I study the Southern Ocean, they're like, why? And I always say, well, why do you rob banks? Because that's where the money is. Why do we go to the Southern Ocean? Because that's where the heat and carbon uptake. This is where the fate of Arizona will be decided. I know that sounds dramatic and ridiculous, but it's true. Our world is so deeply, profoundly, amazingly connected. And I have to go there in order to see what will happen here. So the Southern Ocean is a critical and precarious carbon cycling engine. Once upon a time, the Southern Ocean was just taking up this half of the carbon absorbed by the planet's seas. Strong winds push surface water away from Antarctica towards the north, and then the deeper water rises. You can't have a hole in the ocean, so if it pulls it away, then there has to be water that upwells. This water upwells from far, far deeper than anywhere else in the global ocean. Used to be that we thought that maybe the deepest water upwelling was from maybe 600 meters or 800 meters. You know, it upwells around Antarctica from between 2,000 to 3,000, 20 to 30 football fields, basically from the deep, black, inky abyss up it comes because of these intense westerly winds that drive the water away, creating a divergence that must be filled by the ocean below. That means that these extreme winds are actually tapping basically at the rot of ages, the poop and dead bodies that have accumulated in the deep ocean and been remineralized by the bacteria back into their constituent parts, back into the dissolved components. It's rich in carbon. It's rich in plant food. And that's very important. All that plant food coming to the surface is great. It then gets exported around the global ocean. 75 to 85% of all of the global ocean productivity happens with using nutrients, plant food that came up around Antarctica. But when they live and are eaten and pooped, they basically, all of that carbon gets as it sinks, is eaten by the bacteria and turned back into its constituent parts. Only about half of 1% of everything that grows at the surface ever makes it to the bottom. I know, wild, right? So most of it is eaten by the bacteria on the way down. So it's been accumulating all this poop and dead bodies, the rot of ages, the carbon rich. So our atmosphere has about 600 petagrams of carbon in it, but our deep ocean has 24,000. It's profoundly the deepest, wildest, most incredible reservoir of carbon on Earth. And when the winds blow harder, more of that comes up. That's a worry. So, one more thing. So it's not just a Southern Ocean array. SOCOM was the kind of the pilot project, the regional pilot project. But now my colleagues have an incredible array globally funded with 53 million bucks from the National Science Foundation to put out floats around the world. And these are they. This is our incredible and amazing team. My dear friend who was one of my, was on my committee when I was in grad school once upon a time, Lynn Talley, the most laureated oceanographer alive today at Scripps Institution of Oceanography, and others here. Ken Johnson is the lead on the array. It's just amazing what we're doing. It's a revolution in oceanography. So this was our global biogeochemical array. You can see that, you know, there are more floats in the Southern Ocean than anywhere else, and that's because of SOCOM. But we are starting to fill in the rest of the world through this array. That's me in the pink scarf. This is in Villefranche. This is 9 out of the 10 float deploying countries and their science representatives hashing out the rules back in 2012. It was really fun. So we can do the carbon flux from these floats. This is one of the first papers using floats to do a global, this is the SOCOM sort of result. This is Allison Gray. She's a professor now, assistant professor at the University of Washington. She's just doing amazing. This is what we're worried about. In the Southern Ocean, the water upwells. Basically, you can see these chimneys of very rich carbon water coming up to the surface if you assume this is Antarctica. And so when we look at all the float data, and here you're looking at all the float data, the blue is where it's going into the ocean, the carbon's going in, but the red is where it's coming out. So imagine you were doing that carbon dioxide removal project, and you were like, see, we got them to take up all this carbon in seagrass or in algae. And I would be like, well, okay, when it was pooped and died and into the deep ocean, how long till it came up? I know, I worry about that too, especially with our stronger winds. So what we're doing is we're assimilating all that data, all that new biogeochemical data that we never had before, our pH, our nitrate, our oxygen. We're assimilating all of that into what we call a biogeochemical state estimate. It's really a reanalysis where you take the model results and you nudge the model to as close to reality as possible with every scrap of data you have. And with all these floats, we have a lot more data. So it's very exciting. And this is the first ever of its kind. We never had, remember all those blank spaces? That was blank spaces, and even the physical measurements. The chemical and biological measurements were even sparser. So we finally have enough to be able to do this. It's very exciting. So we did an experiment in our climate models. I'm a nurse system modeler, and Ben Bronsler, who was my postdoc, who is now off to fame and fortune in London, and he did these experiments that we had set up for the IPCC last report in support of the Southern Ocean Model Intercomparison Project, where we changed the winds and look at how much upwelling there is. He did one where he changed the winds, and he did the exact same thing, and he changed how much fresh water was melting off Antarctica. And then he did one where they combined both of them and said, which one of these matches the float data best? It was the one where we combined the increase in the wind with the fresh water from Antarctica. Those two together gave us the best representation of what our floats were telling us. I know, it's so exciting. Better prediction could lead to better outcomes, longer forecasts for us here in North America, and a better understanding of where all that carbon is going. And it matters. It matters a lot. This is an array of models actually being run forward in our IPCC 6 report that just came out. And depending on which model you use, the amount of carbon going into the Southern Ocean is the equivalent of 100 ppm error. We have some that are very high at 254 and some that are very low at 143. And these are the best models in the world. So I'm concerned. I'm ready to keep working on this. And this model that I showed you earlier, the simulation of our glorious and amazing blue planet, this is FE3. This is the finite volume core model from the Geophysical Fluid Dynamics Laboratory at NOAA. And 3.5 years ago, NOAA adopted this climate model as the weather model. So if you got your forecast from NOAA this morning for your storms, et cetera, from your snowfall, you got a forecast from a climate model, not from a weather model at all. And so we've converged our climate and weather models. And actually, we've replaced the weather model with a climate model, because a climate model doesn't just do the atmosphere, it does the ocean too. And that ocean component is the fun part. It's the part that is adding a lot of predictability, because our ocean, we think there might be, you know, our hurricane forecasts are 5 to maybe 7 days. We think that there's 56 days of predictability in the ocean. So here's where we might actually improve this. So we've made real progress towards near real-time carbon accounting. 15 years ago, we didn't have a Supreme Court ruling that the Clean Air Act includes carbon as a pollutant. We didn't have an international political agreement to address the carbon cycle. We didn't have carbon observing satellites. We didn't have an Earth system model that included carbon. And we didn't have carbon sensitive floats that could give us the answer in the ocean. Now we have all the pieces. And while we're not quite to this is where I want to go. This is a simulation, remember, but what I want is a real-time ocean carbon accounting system where I can count and track and measure every molecule basically in near real time in support of our Paris goals, and also in a way that will help us do better forecasting, do better weather prediction, which can help us adapt more quickly, get out of the way, you know, put up the plywood when we need to, and make wise decisions about our resources and our planet. So what comes next in my lab, and I hope across the country, is we'll continue to build out our carbon observing and prediction system. We'll complete the implementation of the near real-time carbon accounting, and we'll publish the top 10 economies' monthly carbon kind of bill, you know, their impact on the atmosphere from basically burning and dumping. And hopefully make this a better place for our kids and our grandkids, and for us. And that is all I had for you today. This is just a little animation of us deploying this and how it works together with our satellite systems to try and give us a better look. Thank you.
Thank you so much, Joellen Russell. That was great talk. And I'm sure there are plenty of questions. We see some hand clappings, and we're going to look for some hand raising. I'll remind people they can raise their hand by going to the reactions panel at the bottom.
Oh my goodness, there's 300 people here. Woo!
Oh yeah, they've been pouring in throughout. And then they can also send me the question
Yeah,
in
come
chat.
on, hit me. Let's have it.
So we got some. Well, let's start with this hand raiser here. Let's see who we have. Although I can't see who it is exactly. Michael. Okay, I'm going to ask Michael to unmute.
Hey, thanks, Dorian. Hey, Dr. Russell, could you address the role of ocean floor methane hydrates and the possibility that the upwelling of those is going to lead to catastrophic conditions? Thank you very
You know,
much.
I get that question a lot. And um, I'm a chemist, actually. So when you look at the equation for the steady state methane hydrate, it's almost entirely, not all, but more than 95% dependent on pressure, which doesn't change. In fact, with more sea level rise, it might actually get more water over its head. So I think it's very unlikely that we'll have catastrophic release of methane from methane hydrates simply because the pressure is what is keeping them hydrates. If you had a profound and abrupt warming or a landslide or something that disturbed them, you could see a methane hydrate go off, but it isn't going to happen as a wholesale thing in our ocean. It's the pressure that's keeping them there, and the water's not going anywhere.
Okay. Thank you. I'm going to go to one of the sent-in questions from Nirav. In the chart showing CO2 levels on the volcano and South Pole, the trends were the same, but one showed cyclical increases and decreases. What causes that cyclicality in only one of the locations?
Those are trees. Those are deciduous trees leafing out. A tree is made of carbon, and it basically makes its infrastructure leafy green. The gorgeousness is made out of air, made out of the carbon dioxide. It literally harvests the carbon dioxide and puts it into its leaves, which draws down the CO2. And in the winter, when it, in the fall, when it dumps and rots, or we burn them, or they're eaten by the bacteria, that they release that CO2 back out. It's deciduous trees. And since there's so much more land mass in the northern hemisphere than there is in the southern hemisphere, which support these big, beautiful trees, that's why we have that spiky piece in the northern hemisphere and not the southern hemisphere. The trend is just our emissions, but the trees have this glorious wiggle. I know, isn't that amazing?
Trees they're good for everything.
They're good for everything.
They really are. We have a question here from Julio, and I'm going to ask to unmute yourself, please.
Hello, ma'am. You touched on this earlier. When you go on an expedition, you have to take everything with you because you can't do anything about it if you forget. So a less serious question that I have is, what is the thing that you regret forgetting the most when you went off on an expedition?
Oh my God. I know right off the top of my chapstick. I kid you not, working out on a deck in these kind of seas. And you have to imagine these, my longest cruise was 56 days. I think my shortest one in the Southern Ocean was 32 days. And just by the way, people get a little squirrely after about 28 days. There's always some drama. I get very zen, but not everyone is like that. And chapstick. Antibiotic ointment for scratches and blisters. Oh my God, I bring bricks and bricks of chocolate to bribe the crew. Don't ever leave without extra coffee beans to chew, as well as instant coffee, the good kind. I bring enough Starbucks Via to float a boat because I'm exhausted. When I'm running the lab, if everybody does their part, then I get some sleep. But if there's somebody sick or somebody can't do their job, or they just, sometimes our students just like, I've had enough, please. I want to be done. I'm like, I'm so sorry. That's not how this works, but go ahead and have a nap. I'll sleep on the floor on a beep to change the titrator out every 35 minutes, right? I'll sleep on a beanbag as the ship rocks and rolls all around you. It's crazy because oh my God, on a good day, when you're up in the crow's nest, it's just a little spritz on the window, right? On a bad day in the Southern Ocean, it's blue. The wave, you chug up the side of one wave, shoots down the other side. It's almost 0 G. You're going for a while. It's like skiing. You'll dig this in a 300-foot ship too. These are not little. Dig the prow into the next wave, and the mountain of water will proceed to fall on you. and crunch the ship down. You feel like you're being crushed like a beer can. Honestly, it's all a metal ship. You can hear everything, smell everything. Oh my God. If you ever think you're lonesome for sea, just put a leaf blower on your dining room table and leave it on for a week. You will not want to go back out to sea on a ship ever again, I swear, because the engines are going all the time and they're straining and straining, and you're hanging on to your food, you're hanging onto the walls, you're hanging onto your chair, you're hanging out in the shower. Let me tell you how disorienting it is to shut your eyes to rinse your hair when it is rocking and rolling the whole time. It is, the weather down there is insane. I thought I had seen blizzards because I grew up above the Arctic Circle in Kotzebue, Alaska, and I'd seen blizzards. But the winds in the southern hemisphere in the westerlies are 30% stronger because they don't have mountains that create friction and speed bumps. So the winds down there are insane. The waves are 100 feet high, and that's not a joke. That's not like a record. It happens in the really intense storms in the winter. So yeah, chapstick. I know that seems crazy. I also had cotton gloves. Don't ask me why. I was a moron, but I was. And what I really needed was high performance sort of climbing gloves. And I didn't have them because when I was in grad school, I was very poor. And that was, oh my goodness, wool gloves would have been fine. But you can't imagine how cold your hands get, how cold your feet get, how tired you get. And you can't afford to have anything break, because if it's broken, you're done. You're done. There's no more measurements to be had. And remember that with climate on this kind of trend, you miss, it's gone forever. You can't come back and try and make that up. It's a different day. You're putting your foot in a river that's already gone. So you asked the best question. Like, what did I miss? Oh my God, coffee, extra shampoo.
It sounds like you could be a good consultant for movies that are doing cataclysmic environmental themes.
Except it's real.
I know. Sadly, worse than fiction. We have a question from Chris, who says, though you may have already answered this, not sure. You mentioned that during the pandemic, the atmospheric carbon continued to increase because the ocean temperature increased. Can you expand on what that means and what that has to do with the pandemic? Thank you.
So during the pandemic, we really reduced our travel. We didn't reduce how much we burned or used in our homes because most of us were stuck at home, but we didn't drive. And that means that there was a significant chunk of the total carbon we would normally be blasting out into the atmosphere that we didn't. The air was cleaner in New Delhi than it has been in 30 years, maybe ever. It was incredible. The atmosphere was bluer. It was amazing. It also happened to be a very hot, very dry year. And we had wildfires worldwide. I don't just mean here in California. We also, and in Russia, we also had them in Australia and in the Amazon. It was burning like crazy, and that's probably where the bulk of that extra CO2 came out. But we also had what we're now calling a hot La Nina. Usually a La Nina is when the winds blow a little stronger along the Pacific equator, which tends to create more upwelling, which tends to upwell colder water, which actually we usually have a little bit slower growth of warming during a La Nina because the ocean is actually slightly cooler and is basically working like an air conditioner for us. However, for whatever reason, in 2020, we were in a La Nina. We're still in La Nina. It's still even hotter. We're having what you might consider a hot La Nina again. Very, very strong winds with increased upwelling, but it's warmer. I know. So it's everybody keeps saying, well, we know all the climate science. You don't have anything you need to work on. I'm like, oh, I wish that were so. But and we do know the basics fundamentally. But we need to move to real time. We do.
And it's changing in real time too, so.
That's right.
Yeah. Freddie asks, could you explain what is meant by the term carbon budget? Does that refer to the Earth's carbon cycle or the carbon budgets of various nations?
I use an Earth system model, which I'm assimilating all of the data in. So what I have is we have what was the amount of carbon available for our atmosphere and ocean before we started burning everything in the Industrial Revolution. That CO2 curve means we've been increasing our emissions over that time period. Although in Europe, they actually peaked, EU emissions peaked in, I believe it's 1998. And in the US, we peaked in 2007. Now, other countries like Russia, Brazil, India, and China have had big increases. And China, of course, is the absolute, they were half our emissions in 2000. And by 2010, they were double. I know it's hard to imagine, but they were building a coal-fired power plant per week in the peak there. So when I talk about a carbon budget, I mean, I want to know where all of the molecules are in the atmosphere and in the ocean. We're basically doing an equivalent of statistical sampling and assimilating that data into a dynamic model so that we can track flows from box to box all over the world in the atmosphere and the ocean, and then attribute the amount of emissions from the surface in each country. Yeah. So when I say budget, I mean a planetary budget that can be carved up into little tiny boxes so that I know where the atmosphere is, where the ocean is, and where individual countries geographically, their exclusive economic zone is their problem. What did they do to the atmosphere? I know that sounds terrible. And I once had a meeting. I was once invited to be on a panel for the National Academy of Science, and I was so proud to be there because on the left of me was Peter Tons, extraordinary atmospheric chemist who had been doing carbon dioxide emissions and measurements at the National Center for Atmospheric Research, and National Academy member, extraordinary human. And on the right of me was Inez Fung, who had been doing Earth system modeling and had helped with the launch of the OCO2, the carbon observing satellite with NASA. So I'm sitting between these two, and I'm there with ocean carbon floats right in the middle, but I'm significantly younger and less well known. And this young person, I had to look him up. He was 26 and he was on the climate negotiations team for the Obama administration. And I said, well, we need to do these things because we need to verify. Here's our atmosphere, here's our satellite, here's our ocean. We're ready to do this. We need investment in order to make sure that the United States can verify this the way we would verify a nuclear treaty. And he looked at me and he said, I'm sorry, but we need to tell you that you really can't use the word verify. Other countries might find it punitive sounding, so you're not allowed to use that word. You'll notice I put it all over my PowerPoints now. I just like, you're 26.
Yeah. Has any ever heard of trust and verify?
Oh my God, I have just like, I almost came over the table. Peter and Ezra were like, Joellen, just sit down. It's fine. I was like, fine. But yeah, I want to verify. Yep.
Of course, that's science. Let's get a live one here from Animus Rex. Animus Rex, we are curious. Unmute yourself to hear what your question is.
Hi, thank you very much. I saw a report that the Southern Ocean upwelling is melting the bottom of the Antarctic ice shelves. Can you speak to this?
Yes. In fact, I designed the Southern Ocean Model Intercomparison Project as a pet project of mine that I got my friends to basically include in our IPCC sort of intercomparison model simulations, because none of the scenarios that we're currently using to forecast our climate do these projections for the IPCC. Did you know that none of them include melting from Antarctica or Greenland? Yeah, I find that it matters. It's a big deal. So that upwelling, that more intense upwelling that I was telling you about because of the increased winds, that more intense upwelling is bringing water. Now, remember, everybody's like, but isn't the water really, really cold? Yes, it's really, really cold, but it is above freezing, right? The ice isn't freezing. The water is above freezing. So if you put, ice cubes in your warm drink, they are going to melt, and they're going to melt faster than if you just set them on the table, because the heat capacity of water is so insanely much larger than the atmosphere's. So yeah, it's like putting a fire hose of warm water underneath the ice shelves, which has demonstrably thinned out. The caverns are not just little caverns anymore. They're great, big, wide thinning underneath the ice shelves. The other part is that as we put more fresh water, I'm sorry, I'm going to bore you guys to tears, but you asked me the question that I totally love and know the answer to. So we put all this fresh water in, melts in, sits on the top. It takes a while for it to mix away. And that means that, we're trying to push that water away with the winds. But what it does is it basically traps some of the heat from getting all the way to the surface. And it traps it at roughly about 600 meters. Want to know where the ice grounding line is for the really big glaciers in Antarctica? It's sitting underwater at 600 meters. And the potential increase in temperature that we project from our models when you add the extra winds and the freshwater input, remember I was telling you about that experiment? It's almost 4 degrees warmer when you put that cap on and you increase the winds. And it absolutely is the best explanation we've ever had from a model for the data from our new floats. Seriously, it's happening right now. So if you read that incredible New York Times article about the Southern Ocean that was on the front page of the New York Times, it was so awesome. I can't believe it. We've been saying this for a really long time. I've started going to sea around Antarctica in 1994. And it's very hard to get above the noise. And I think we're finally there. That felt like a watershed. Keep asking me. These are great questions.
It takes a catastrophe.
This is amazing.
Oh, we got some more. Actually, here's a question this fellow John has that's related. He says, I read a recent article from Cardiff University that melting icebergs are key to triggering a natural ice age cycle. Warming of the ocean, though, interferes with this. Did you have any thoughts about that study or have any requests for data to support this idea?
So I've never heard of that, mostly because icebergs are basically chunks of the ice shelves breaking off into warmer water. And I'm not sure how that would ever, I have icebergs in my climate models. I bet you didn't know that. We actually have icebergs. It is numeric. We started out with sea ice that were kind of like hockey pucks, but it's gotten so much better since the old days. And we actually, because we want to do sea ice forecasts, so we've been working on this really hard, and the breaking off of the pieces that becomes these big icebergs, et cetera. We have these slushy bergs that do melt, but I don't know of any feedback that would, because of course, if you're breaking pieces of the ice shelf off, you're not increasing the albedo, you're decreasing it, which should make it warm more. You're getting more ocean area, less white area. You're putting it into more water, so that should melt faster. It's got more circulation around it. It should melt faster. It's being pushed north into warmer water, so it should melt faster. I don't know how that could cause anything like a glacial age. I actually have written a lot and done a lot of experiments on glacial to interglacial and what happened. And it was a change in the winds. When we decrease in a lower CO2 world, when the atmosphere is slightly cooler, it basically shrinks down a little bit like a balloon. And you basically see those snow lines on your mountain peaks basically crawling down the side of the mountain. So less CO2 basically makes them come down. And when you move the winds away from Antarctica and weaken them, the upwelling weakens. Now, remember, I told you that most of the poop and dead bodies, the 24,000 petagrams of carbon that sit in the ocean, there was way more of it during the last glacial. And that's because when we move the winds away from Antarctica, just naturally through insulation changes with the tilt and wobble of our orbit around the sun, these are 26, 43,000 type timescales, very long, doesn't do anything today. The insulation change, remember, Irby's still looking. So the short term, this has nothing to do with what's happening now. But in the past, when we had this tilt and wobble, the winds moved away from Antarctica, the westerlies moved away from Antarctica and weakened slightly. And that meant that we had less upwelling. And with less upwelling, more of the carbon stayed in the ocean. And that's why it kept getting colder, is because more of the carbon is in the ocean, no way to stir it back up. It gets a little colder and this carbon stays in. It gets a little colder and the carbon stays in. It gets a little colder and even more goes in. That's how it works. So when you look at the seesaw pattern that you can see in our glacial, our records from ice cores of how much CO2 there is, starts at the interglacial, comes down, comes up, comes down, and it takes about 80,000 years for it to get all the way down to the maximum glacial, and then it stays down there for a while, and then it pops back up. Want to know what happened to pop it back up really abruptly, roughly 200 to 500 years like that in geologic time? We hit an insulation cycle where the winds moved slightly poleward for longer in the winter, which started burping CO2. It had filled the reservoir full of carbon within 400 meters of the surface. The winds picked up, it burped some CO2 out, which increased the amount of CO2 in the atmosphere, which warmed the atmosphere, which intensified the winds, right? Which then burp more CO2 out, which intensified the winds, which burp more CO2, and boom, we're back in the interglacial. So the last glacial for our planet for the next millions and millions of years, that was the final glacial age. There will be no other. We've put so much active CO2 into the atmosphere now, and it's spread through the ocean. There will never be another glacial.
I'm going to ask DN to unmute and give you a moment there to have your water to unmute and ask your question, please. DN.
Good morning here from tropical Singapore, sending you guys some warmth. Dr. Russell, thanks so much for sharing your fascinating work, the work of you and your colleagues, and Science Club for giving you a platform. Many questions, but I think what's most intriguing, you are talking about this real-time ocean carbon accounting system, right? An amazing project. Where are we now in terms of reaching near real-time coverage, and what are the biggest kind of speed bumps for the work of you and your colleagues to achieve
the
this?
checks in the mail. That is my favorite question. So I just got a proposal turned down. I had applied for $200 million to NASA to build another wind satellite and deploy it to do polar orbit over the Southern Ocean. And I'll tell you why. We are only getting about 2 measurements per day per location on planet Earth. Now, think about how quickly a hurricane spins up and how fast it moves. We're only getting 2 measurements per day. And remember, around and around and around. So first we needed Southern Ocean measurements. So I went to sea to do them by hand, carbon. Then we needed robot floats. We got those all deployed. And then we got our big global array funded, and those are getting deployed. And now what I really need is I need to go from 2 measurements of a day to 4, to go from a 12-hour window. That's too long for really abrupt wind events at anyone's house. You know when the peak winds are, and they only last 3 to 4 hours over your head. That's the problem. We're missing our peak winds. We're not getting them. Because we're only looking every 12 hours, and that's just not enough. And the peak winds have a nonlinear effect on carbon flux. The air-sea gas exchange is much faster at the highest wind speeds than it is at the lower wind speeds. So the bulk of the gas transfer is really happening at the higher wind speeds, which, by the way, is where we're headed with climate change, the dynamic effect on our atmosphere. So we have way more high wind speeds, and we're not looking often enough to see them. So I need to do that budget, both an energy budget, a carbon budget, and a heat budget, in order to really know. And I'm missing too much of it. So we put in a proposal to do just the Southern Ocean increase. And it has been suggested that we submit not just to this Earth Venture Mission class satellite, which would just give us a regional satellite, but they said, same as with the robot floats, in about 18 months to 2 years, we'll be applying for a global class wind satellite to go from 2 to 4. I would have preferred to get started sooner. And the reason I say that is, in real time, I need the budget. I'm missing a component of the budget. And with our current set of satellites, I will never get it. There is no way to make up for not seeing the peak winds. And just by the way, so they've got all these other kinds of satellites and constellations. Everybody's like, we'll use the other wind information. I'm like, okay, 1, none of those reach the Southern Ocean. Two, when they do reach the Southern Ocean, their return time is every 16 days. This is useless to me. I need real-time carbon budget, and I need those satellites to get it. I'm sorry, I don't mean to be cranky, but like, I will get there. I will find a way to get my scatterometer up. I have all these amazing colleagues. They've been incredibly helpful. We did very well. They gave us low risk, that there were no major weaknesses in any of our technical. So I am hopeful that we will get our array of satellites so that we don't miss our peak winds and we do get our full carbon budget in real time. Okay, after that, I want to do better in our coastal areas. The transfer of carbon out of rivers and away from our coastal exchanges needs to be done better. So what we really need are gliders that are nationally deployed. See, the problem with that is anything that is driven, again, can only be funded and deployed by the country that's doing it. And most of the coastlines we don't control, and the US would not be welcome to run the gliders. But at least for the US, including Alaska, we could probably talk to our colleagues in Mexico and Canada, we could probably get mowing the lawn to actually look at the exchanges of carbon and materials on and off the shelf. And so, I mean, for me, the main problem, the bulk of the problem is the air-sea gas exchange that I'm missing because of the winds. Now that I'm going to get my global float array, I'd also like to make the float array denser. Right now we're going 1 every 4 degrees, and I think that is just barely adequate. I would like to do maybe even a little denser. So there's plenty to do. We had hoped that our international partners would make up half the array, and they really have not. I know it's pandemic and everyone seems to be claiming that they are broke, but less than 5% of our BGC floats out right now that meet our criteria are funded elsewhere. Now, of the Argo array, the temperature and salinity floats, half of the array is supposed to be. It's only 42% because our floats last longer. I know. Would you like to know? Can I say something terrible? Would you like to know whose floats have the poorest engineering and last the least, are the least robust? Yes. The Germans. I shit you. I mean, I'm not kidding. Seriously. Ha 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 ha. And the American floats last almost 10 years. It's really quite remarkable. It's just effort, elbow grease, innovation.
Well, that's surprising given their
I know. They'd like to convince you that their engineering is better, but it's either their engineering has a problem or they're just not investing appropriately.
Maybe. Let's hope there's some funders out there listening about it. You actually, and this dovetails nicely because we had a few questions about robots floats, and one was about the size, and if that was the same size that was seen in the video. One was about the cost, and if there's any interest in funding, and also about the recycling. Are they recyclable, recycled?
So I'm going to start backwards and say the recycling ones we've thought a lot about, and we made the housing edible. We made as many of the parts edible as possible. So within 10 to 20 years of landing on the bottom, they'll be eaten. And it will just be a handful, less than a handful of metal parts that will actually still be left on the bottom. And the rest will just be eaten. I know that they are the greenest possible that we could make them. We put a coating on it that's supposed to last 10 years to protect it from UV and other stuff. But of course it's down dark in the black inky abyss. So it wears away and then it's eaten. I know, edible. You can't do that for space junk because they don't have bacteria to do the eating. And they're about you saw in the video my student Becky, who is 5 foot nothing, and so the float's a little taller than her. That's the standard size, and let's see, they're a little different shape if you do the deep Argo ones, but those don't have chemistry on them yet. It turns out that if you go below, the reason we limit them to 2,000 meters is because some of the sensors get crushed, don't do well under heavy pressure. So it's an interesting. What was the other one? There was something else besides size.
Recycling cost and interest in funding.
we had hoped that the cost would come down faster for the floats. Now we're in the headwinds of, sort of inflation at the moment. But part of the problem is that certain manufacturers are pain in our rear ends. They increased the price of one of the cables we need, which is just, it needed to be RF shielded plus salt resistant plus. So they had something that really worked for undersea work, something else. But they started charging us, instead of $2 for the cable, like $1,000. I'm not kidding. I'm like somebody's insulin kind of jacking up the prices. So it's been difficult because we're not currently deploying enough of these to really make a big economic impact, even though we're hoping to kind of save the planet, right? A carbon budget that doesn't include the 72% of the Earth's surface that's ocean is useless. Maybe not useless, but there's enough leaks there that you could drive, 10 coal-fired plants in China through it. And I literally mean that. That's how much wiggle room there is. It's a lot. And so we need to do this, but we're kind of struggling to get good manufacturing, good supply lines. And then of course, nobody wants to go through the 21 different tank tests that we put our floats through before we deploy them. We need them to do their work all alone in the inky darkness, far, far away in the deep blue sea, all alone for 5 to 10 years with no help from us. Now, it turns out the software is amazing. And since it actually communicates by iridium satellite, you can download new code onto the floats. We actually change how deep they go sometimes if there's something we absolutely have to see. I know, it's amazing. That's how they avoid ice, because they could come up and bang their heads on the roof of the ice, of the sea ice that grows around Antarctica every winter. So what it says is 2 lines of code. Hey, dummy, if the temperature sensor says that it's changing really fast, go back down. Genius. So cool. All right, did I miss one?
No, I think you got all that. I was just saying it's shameful that they would be gouging you when you're trying to help save the planet there, but
it's true. But on the other hand, these are things we think we can work out, and we're grateful for the opportunity to sort of raise the profile, because every time we make this more public, at some point they're going to want to slap our stickers on their websites and say, hey, we're helping, now that hasn't happened yet. They have huge defense contracts that are way more important than ours. But we're hopeful that that's how this will go. We're hopeful that the rest of the world will see it and start investing as well. But to be completely honest, I don't care. We'll do it ourselves. The US can do it. We have both the scientists, we haven't even gone outside of the normal funding. This isn't congressionally mandated funding. We competed for this through the National Science Foundation, through the National Oceanic and Atmospheric Administration, and through NASA. So we're not even, nobody told them to fund us. We went and competed for this funding, and our colleagues agreed that this was the most important thing that they could be investing in. So don't worry, we got this. This is not too big for us. If Walter Monk can help save D-Day, there is nothing that my community won't do or lay down in the road to get this done.
that's great and reassuring. Now, I'm going to check with you how you're doing for time with the Q&A here.
I'm fine. How about 10 minutes and then we'll call it good? So
Got
get
it.
them in there if anybody
Got
else
it.
has others.
All right, well, we have a live one here. Gabriel, I'm going to ask to unmute. Or Gabrielle.
Hi, thank you so much for this wonderful talk. I read a story recently about concerns in the Northern Hemisphere that melting glaciers were adding too much fresh water to the Northern oceans, potentially screwing up the way that differences in salinity drive ocean currents. I was wondering to what extent that is also happening in the Southern Hemisphere. I'm sure your robots are picking it up if it is happening, and how that interacts with your wind studies.
Oh, this is an excellent question. So most people on planet Earth don't realize, but every single major current in the world, except one, is speeding up. The winds have picked up, and that's what primarily drives the stirring of the ocean. It's not I mean, heat and freshwater matter, but the first one, the big one, is just the wind pushing the water. Force equals mass times acceleration. There's a lot of force. It keeps moving the water. But the one that isn't speeding up is the Labrador current. And it's not speeding up because we're dumping a crap load of water off Greenland. And it's just what they call ramping up the hydrologic cycle. The westerlies are carrying more water vapor because it's hotter atmosphere and it can hold more. So when it rains or snows, it dumps way more, which is why it's dry for long periods and beautiful and gorgeous and way too hot. And then all of a sudden, whoop, it just dumps and dumps and dumps. And that's it. So the combination of melting and, you know, of the Greenland ice sheet and all the rivers that flow into near the Labrador Sea up here, that is actually a really big deal. Now, once upon a time, there was this idea that if you put enough fresh water into the North Atlantic, that you could stop the overturning of the formation of North Atlantic deep water, which is that deep water that bloops down in the Greenland, Iceland, Norwegian Sea, and then flows back along underneath the Gulf Stream, which is along the coast there. Now, two things is if you read that in the New York Times, if you read all the way down to the end of that article, I know they've had 2 ocean-related articles right on the front page. I'm like, oh my God, woo! Now that one, if you read all the way down to the bottom of the article, Susan Lozier, who's now a dean, was at Duke and now is a dean at Georgia Tech. She's an extraordinary oceanographer, and she's the one who got the OSNAP array funded between Greenland and Iceland and the UK to actually look at if that was changing. And if you read all the way down to the bottom here, she says no real oceanographer believes this, that it's actually slowing down because we have measurements of the speed and it's not. We've dumped a lot of fresh water in there and it hasn't. Now, under pre-industrial conditions, without all the human emissions, it's possible that that mechanism might have been important in the past. So when you read up higher in the article, there's a lot on paleoceanography, which is pre-human interference sort of oceanography. And that might have been possible. Today, it's just not. Because the warmer it gets, the higher the winds, the bigger the overturn. Yeah. I know.
We're getting a lot of questions about the robots.
Oh,
one wants to know what kind of sensors are in the floats. Is it just detecting carbon and wind levels, or are you also doing chemistries and biological? And then James wants to know how many number of total floats used to help create the data.
So each float has pressure, temperature, and salinity. And it drops to 2,000 meters every 10 days and does a full profile to the surface and then immediately beams that data back. So that profile is completed and reported at the same time, right? And the sensors, in addition to the temperature, salinity, and pressure, which we have a big array called Argo, which is the 3,000 floats that just does the physical properties, just those. Our floats have 2 optical sensors. One is chlorophyll fluorescence and the other is backscatter for how many particles. And we use this to look at blooms and ecosystems because particles, poop, and fluorescence growing, right? So growing and pooping, we got these 2, right? And then we've got nitrate, which is plant food. We've got oxygen, which is both a product of photosynthesis and a requirement for bacteria, whales, and all of the rest of us. It dissolved oxygen. And then we've got pH, which actually, because of acidification, it is a carbon parameter that we can use with the salinity, the oxygen, and the nitrate to actually calculate what the carbon is. So we don't directly measure the carbon, we measure the pH. And that actually, the pH is dropping. And it's not just dropping in one spot. If you look at 12 months of float, in the 13th month, so I get from here to here, from January to January, in the same location, it will be lower every time. It takes 2 years of data to see the human impact on the ocean if you're measuring pH. That's not a joke. Ugh. I'm sorry, but that's like the most depressing thing. But I can see acidification in real time all over the world ocean. So currently we have funded 500 global floats and 400 in the Southern Ocean. We need, but these die after a while, right? So you have to keep renewing the array if you want to keep looking. So, so over 5 years, we're going to build out this 500 float array worldwide. And we think that's roughly what you need in order to see the global budget, get a budget. Now, to refine that budget, I need to fill that in a little bit. I think I'd really, we've done a bunch of these observing system simulation experiments, observing system design experiments, where we take a model, we subsample it with floats, and then we add a few more, and we see if we can reconstruct the field. How close to the ocean that we simulate can we get by sampling? You know, how many samples do we need to get a good picture? And I think 500 will do, 800 would be better. And really, it's so little money. There are other things we could do too that would help. Like apparently Boeing actually offered to put carbon dioxide monitoring equipment in the nose cone with all of their air quality monitoring. But NOAA didn't have the money to give them the equipment. So all US flagged planes, not just the Boeing ones, could be doing profiles up and down of carbon dioxide in the atmosphere all over the world every time they fly, but they're not. I just find that it's cheap, it's easy, it's normal, and we need this real-time accounting, and it would really give us some incredible data.
It's very wasteful.
It is. Now imagine, you know, it's not just into US cities, it's into Beijing and New Delhi. It's into everywhere we send our planes. And they're allowed to monitor the air on their aircraft. It's like my float cheat. I mean, it's not a cheat, it's an agreed on UN program, right? But it's also agreed that you can monitor the air quality on your plane. So here's how we could build a world-class system that would actually do detection and verification in a really incredible, easy, straightforward way, and a massively cost-effective and minimally damaging. Woot, wouldn't that be fun? We could do that right now. There is no tech required. It's already here.
Seems like you just got to sell them on the sort of, we're pulling one over on Beijing and everything by doing this, and then maybe free data.
Honestly, it's I don't see the downside here. I really don't, and I keep hoping that that this will be. Right now, we're just competing for funding, and I'm happy to keep doing that. But it'd be great if Congress got off their duffs and actually made. You know, here's one more thing that's annoying me. So sorry, everybody. One more thing. So did you know that we don't have an ocean forecast system, a civilian ocean forecast system in the United States? They do in Europe. The European Center for Medium Range Weather Forecasting is on Ocean 5, Ocean 5.0. We're on Ocean 0. We have great ocean models. We run them in our climate models and all the rest of it, but we don't have operational forecasting with them. Right, we do this for the weather, but we don't do it for the ocean, even though Europe does it. So you can get, you know, blooms, fish, you know, all kinds of amazing data out of their forecast systems that you can't from the US because we don't do it. They made a decision in 2004 that NOAA just didn't have the budget to do this. So in 2004, Europe started creating Ocean 1.0 and we didn't. And now we're behind. And it would be good if we caught up. But very, very exciting, very exciting. Lots of fun things to do. New discoveries.
Lots of them. But now, would you like to take one last final question?
One last, that would be great.
And someone is asking for the New York Times article link. Maybe Margaret can look that up and post that here. The New York Times article you just spoke about. Post it in the chat. From Paul, he's asking, thanks for an awesome lecture. I'm curious if there's any data or hypotheses about how seismic activity affects Southern Ocean carbon release.
Short answer is it doesn't. However, and the way we know this is that you can actually, if you're talking about subsurface, we can actually see using there are tracers that we use in the ocean to actually monitor how much is being emitted basically through our hydrothermal vents. And the seismic activity tends to have a billow or a plume in addition to what's going on. And so we can actually see how big and important those are. And they're very, very deep, obviously, on the bottom with much less activities near the coast. And the reason is they're covered, they're buried basically in the outwash off the continents. Unless you're on an active subduction zone, which can happen, at which point it's quite deep in the trench. So we do monitor these, and it does take a real ship. You can't do this from a float, but we know where the plumes are. We know how big they are, and we know what impact they are. And generally, there isn't as much carbon. Most of the carbon doesn't come out of these hydrothermal vents. It comes directly out of the volcanoes on the back of the subduction zone, like the Andes or Japan. In a back arc basin or on top of a subduction zone. And so we see those much, and we do every molecule. We look at every single bit. And those plumes are very obvious, and they're not very big, and they're not very strong. So, but we do look. Sorry, if it sounds like I've answered this question because I've looked at it, it's because I have.
Cheat. Well, thank you so much for your time. What a great talk, and amazing answers in the Q&A.
Thank you for the great questions. Boy, what an audience. I have to say, honestly, never gotten such an on top of it erudite audience. Wow, very impressed.
Well,
thanks for having me.
We love our people make us. Our speakers and our attendees are what make the Secret Science special. So, Joellen Russell, what a pleasure to have you, and we hope you'll come back. It sounds like you have enough research and information for several more talks.
We're having such a good time. Come on in, the water's fine. You can follow me on Twitter at Deep Blue Sea Next. Bye-bye.
Okay, we'll make sure they get that information. Thank you.